Hi everybody, I think we can get started. So today Augustine will present on the work he did during his summer internship with us. So with me, Thomas and Colin, so we are in the performance engineering team, and Augustine work on the framework to try Fortran. He is in the last year in some college, I forgot the name, sorry. But yeah, and but he will present it. So don't hesitate if you have any question, and thank you for joining. Augustine, you can start.
Yeah, and people can, if they will mute themselves if they're not talking.
Perfect. Please go ahead,
Right.
Augustine.
Right, okay. Let me share my screen here. Okay. Obligatory, is everybody able to see my screen question?
Yeah,
Is everybody
maybe
able to?
can you maybe stop putting the video for the bandwidth?
Yeah, sure. Okay.
And for what? Oh, perfect. Perfect. You can start.
Okay. All right. Hello, everybody. Thank you for the introduction, Thomas. My name is Augustine, and you are here to see my presentation on my Fortran testing framework, or alternatively titled, Surviving an 112-core Pileup. So, to start, let's look at a little background. So about me, I am originally from the small American town of Naperville, Illinois, which is about 20 minutes south of Lamont. I am a senior computer science and history double major at St. Olaf College, located in Northfield, Minnesota. I have background in TAing, tutoring, and grading for an introductory Python course, and currently I serve as the vice president of St. Olaf's local algorithms club, where we present students to encounter questions in engineering interviews. At the start of the project, I did not have any background in Fortran or in Bash because all of my classes, or most of them at least, were encountering C and C++ and Python coding. So, the issue at hand. So, currently Intel is working on a compiler which is currently titled IFX, and they are working to migrate to a structure called the One API project, which includes support for OpenMP, which allows them to port some of their functionality to GPUs. However, their transition from their current infrastructure to this new infrastructure is an ongoing process, which means that there are going to be a lot of bugs along the way. This compiler is currently in open beta, which renders it as bleeding edge, which I'm sure you guys know what that means. The goal of this project then was to develop a testing framework that tests compilation bugs. So we needed a couple of tools for this. First of all, we needed to compile thousands of Fortran files to have a large coverage. So in order to do this more effectively, we needed a scraper to take advantage of public file repositories from the internet, and we needed a makefile generator for directories that need it. Not all directories that are downloaded from the internet have a makefile included with them, so we needed some kind of tool to account for this. We needed to save results from runtime to a record that could be accessed later. It could be that perhaps the person using the framework wants to look at the log of a certain compilation runtime, or it could be that we need to use these logs for cross-checking later. Speaking of cross-checking, we needed some kind of program that facilitated cross-checking in an effective manner, that also displayed outputs in different ways so that people could pinpoint errors in the log and discover for themselves where a compiler may have gone wrong. And with all of this in mind, it's important to keep in mind that we need speed, portability, and accessibility in all things that we do with this project. So the ingredients necessary for the creation of this framework. Now, in order to run the test itself, there are 5 key components that go into the runtime of this test. So first and foremost is Bash. The entirety of the test is run through a Bash script. We then also need Make itself, which facilitates the usage of these different compilers. In my case, this was gfortran and IFX. We needed the usage of the Bash automated testing system, which is a public Git repo that basically takes in a set of Bash instructions and spits out whether or not those instructions failed in a verbose manner. We needed the Fortran compilers in question, so we needed a stable compiler to cross-check against. In my case, I tested against gfortran, And we needed a bleeding edge compiler to do research on, which was IFX. And finally, parallel programming, because using the HPC systems available at Argonne, we're able to speed up compilation by a factor of 112 if we are able to use parallel programming effectively. Also, for pre and post process, we need Python scripts in order to first make sure that these tests for bats exist preemptively and that they are able to be used during runtime. And after testing is done, we can use another Python script to cross-check results against each other and make it easy to detect where a compiler may have gone wrong. So let me get into the process itself. So, first of all, we needed the usage of mass compilation. It was important to ultimately be able to compile Fortran programs in parallel. However, before we could get to this, there were three main obstacles that faced us along the way. First of all, it is tedious to download individual Fortran files one at a time, whether through the usage of right-clicking on a link and downloading, or using wget in a terminal. Additionally, not all directories have makefiles included. And this was something else we needed to account for using a pre-process Python script. Finally, compiling programs one at a time individually is extremely slow. So, in order to account for these three things, there were three measures I took to take care of them. One was a scraper. So, a scraper basically made it a lot easier to download a bunch of data in bulk. And our scraper, creatively named scraper.py, was executed as such. You can see on the slide here. The three arguments of the scraper made it incredibly adaptable because it meant that all you needed were the website URL, the page on which all the links were stored, the path to each individual file, so the URL set of slashes preceding the name of the file itself, and finally the extension to be scraped from that file. So if the web page you're looking at contains all .f90 files, then you can use .f90 as your third argument. So with this, it became a lot easier to download several files in bulk, which then allowed us to facilitate testing more easily. At the end, we downloaded about over 3,000 files. Additionally, it is important to note that it is the user's responsibility to download files with proper licensing before testing them. Secondly, we needed a makefile generator. So not all of these downloaded files from the internet include a makefile. Most of them were just a collection of Fortran files, which could run individually or perhaps fed into one another in directory trees, but a lot of them did not innately contain a makefile that would facilitate automatic compilation. Thus, we needed a Python script that could parse through all the Fortran files in a given directory and find important key terms, which included the following. The first and foremost, you have your exclamation points and your C's, capital or lowercase. And the capital and lowercase was found in older versions of Fortran, but it needed to be able to detect if a line was a comment or not, which would essentially mean that that line is relevant to the overall structure of your directory. It also needed to find use calls present in Fortran, and if there was a use call to a module generated in another file, that means that the makefile was going to need that target for the compilation of this file. Additionally, there were four structures that Fortran defined that don't necessarily make the file at hand an executable, which include an interface, module, subroutine, and function structure. The program call itself designates that a file can be run as an executable, and the end call designates the end to the aforementioned 5. So this makefile generator also required the ability to differentiate between what was and was not an executable. Some files were just objects. Some files were just files which were created to define a module for another file somewhere else. Other files had no definition as of modules whatsoever, but instead used a bunch of modules elsewhere to create a program, an executable. And there were even some examples where a file could do both. Some files had program calls in addition to module calls where they defined modules to be used in other files. So the makefile generator needs to be able to parse through all these things and make sure it knew the difference between the two types of targets. And finally, parallelization, because why wouldn't you compile one file at a time when in the case of the Skylake computers you could do 112? So Throughout my work on this project, I discovered 4 important flags for this specific usage of GNU Make. And this included -J, which, put it simply, enables parallelization in the first place, -K, which prevented parallelization from, or not parallelization, but rather GNU Make from finding one file error and giving up entirely. So hypothetically, if there were a directory with 1,000 files in it, we don't want it to compile 10 files, find the 11th file, run into an error, and then give up. Without the K flag, that's exactly what it does. Now, the K flag does not exactly make the makefile ignore errors altogether. It instead causes them to power through them and attempt compiling everything before spitting out a list of all the successes and errors found within that directory. Additionally, we needed the -O flag. So this was an important flag for facilitating parallelization because it allows the individual processes to run in parallelization, but then it forces the output of these processes to each take turns in displaying their data. Without this, you run into what is essentially a soft race condition. It's not something that necessarily breaks compilation itself, but then the error messages that are displayed as a result of not using -O can be as jarbled as the example you can see on the slide. However, the usage of this flag does require GNU Make 4.0 or higher. So that is actually one of the prerequisites for the usage of this framework. And finally, I found that the --trace flag also came in handy for this project because that causes Make to announce the beginning of each compilation. So with that, it's easy to parse through the log file and understand, okay, this is where an error started, this is where an error stopped, and here is where some irregularities might have occurred in between that start and that stop. With that, we might be able to detect if this is an error or not. So after this is all said and done, the results of this are saved in the name of the compiler .log in the subdirectory logs. So finally, we needed cross-checking. So in the case of my development, I cross-checked IFX against gfortran. So I have tested the usage of gfortran and IFX. We have log files containing all errors from both, but now what do we have to do? So if the compilation of a file failed in both compilers, it's most likely an issue with the file itself. Maybe there was some kind of variable that might have been declared with the wrong type, or perhaps there was a use call that needed to happen that was not occurring, and that's why it happened to fail in both instances of compilation. However, if you are attempting to check results of a bleeding edge compiler against a stable compiler, like in the case of gfortran, and it only fails in your second compiler, it is most likely a compiler side issue. However, how then can we then take these results, parse through all the errors, find the differences between the two, and then get a concise and easy to access summary of the results? And the answer is compare.py. Now, not everybody get excited at once. It's pretty cool though. So compare.py, in my humble opinion, is the coolest thing that I wrote for this project. So it uses the --trace flag to accurately parse through both log files and compilations. It's able to detect error messages and differentiate between error messages and warnings, because it is entirely possible that compilers will warn the user of bad form present within their code, but it might not innately make it crash. It also uses dictionaries to cut down on runtime and make it a whole lot easier to detect differences in errors, because all you need to do then is assign the key name of each file that broke. It also allows for 4 different formats depending on how the user supplies their arguments for its run. So if they use /compare.py with no argument, it prints out a certain way, which is different than if they were to use -b, -g, and -v, which respectively output to a basic syntax, a graph using only the titles of each target, and -v, where it prints out the information of each to a neat table. You can see examples of this in this slide here, where on the left we have an example of the -g flag, and on the right we have an example of the -v flag using 50 columns on each side. So some findings I encountered throughout the making of this project. So, behavior of gfortran. So gfortran is actually able to catch many errors that IFX does not. So for example, in the case of this genin.o object created from genin.f90, which I believe was encountered in the shroud file, we see this dummy argument px. Now gfortran is able to tell the user that there are too few elements for the usage of this element, and therefore it breaks. It returns an error 1. In the case of IFX, however, it compiles just fine and runs into no errors whatsoever. Then, this actually also illustrates something interesting about GNU Make's behavior itself. So, Make will not attempt to compile a file if one of the dependencies before it fails. So, if there is an executable that relies on an object, if the object fails, the executable will not be attempted to compile. So, in this case, we can see a vital difference between gfortran and IFX again. So, again, gfortran catches an error that IFX does not. In this case, there's a silly typo found in the first line of a certain file where somebody accidentally misplaced a 7 before a subroutine call. So gfortran is able to detect this, tell the user that there is a non-numeric character in statement label at line 1, whereas IFX compiles it just fine. Now, it goes on to attempt to create an executable from this file. So gfortran doesn't do anything. If you were to look at the log file for gfortran, there is no case where where make attempts to create triangle linus rule.exe using gfortran. But when IFX was encountering its usage of make, it did attempt to create this executable using the object that was supposedly okay in the past, where it then subsequently ran into an error. Now, a side note, the reason that the make file believes this file to be an executable is because of the nature of my metamake.py, which is the make file generator, wherein a line not belonging to a subroutine, interface, module, or function structure could technically be counted as a program, which is actually something else I discovered about Fortran, is that in the same way that in Python you don't necessarily need function definitions, you can just put everything at the first level of indentation and run it like a main. Fortran can actually behave the same way, which is something that actually caught me off guard, but is an interesting thing I learned about the language itself. And finally, behavior with IFX. So IFX has some limitations with .f77 support. So while gfortran was consistently able to perfectly compile all the Fortran files found in a certain NASA framework that I imported, IFX finds itself running into catastrophic, inexplicable errors in lines such as these. You can see a couple of calls to subroutines and entry points. And you may notice the third example there that there is no right-hand parentheses. That is verbatim. I copied it directly from the source file itself, and so, older versions of Fortran might have different syntax than newer versions. So, out of the 1,791 Fortran files found in this NASA framework, IFX encountered catastrophic errors in 118 of them, which constitutes roughly 6.58%. So finally, some conclusions I encountered in the making of this project. So, some issues. This framework relies innately on the reliance of the stability of a certain baseline. In my case, it relies on the stability of gfortran. It could all the same rely on the stability of something like ifort. But whatever you're cross-checking against, you're basically placing your trust in that compiler's ability to consistently produce perfect results. Additionally, there is an issue of portability. It isn't entirely a repo that you could just download and run without any prerequisites whatsoever. I tried to minimize how many extra tools you would need to use this, but ultimately you need Python 3, Make 4, and BATS in order to facilitate proper testing and usage of this framework. Additionally, if you want to use the scraper itself, you would need to download the beautiful soup Python library. It also relies on all being a valid target for a directory's given makefile. This is actually an interesting nitpick, but it basically means that if you were to download a directory or a repository that has all as a legitimate executable to be compiled, then there could be errors once BATS tries to test the compilation using Make. It also finally relies, the compare.py program relies on Make spitting out more or less the same error message every time. According to the documentation, if Make encounters an error with the compiler itself, it will always return error 1. And in my practice, it did, but As Thomas pointed out, there can be instances where make does not use the same syntax to declare an error with a given compilation. I found in my case that it would always say make, comma, 3 asterisks, and thus it became easy to parse through and find, okay, every line with make, comma, 3 asterisks, that's going to be where there was an error. But because that's not necessarily always the case, the fact that we rely on instances such as those and a couple of specifics that I put in as backup in case that requirement wasn't fulfilled means that if you were to use an older version of make where this syntax was not followed, there could be errors in parsing through and using compare.py. And finally, with the source code of the framework itself, it is difficult to test the functionality of individual functions, such as a function called build directory in compare.py, due to overcomplexity. It would have been wiser, ultimately, or maybe in retrospect, if I had compartmentalized functions even further to enable easier doc testing, and to make it so that it was just simply easier to look at a function and understand what it does. So some things I've learned in the 12 weeks that I've been working on this repo. So it's very important to test frequently. And I'm going into my senior year as a CS major. This isn't necessarily a foreign concept to me, but this was a framework where it really, almost in a meta way, tested my ability to test. It's important to compartmentalize, as I've said, things into bite-sized functions and across several different files for 2 reasons. One is that, as I've said, it makes doc testing possible, which doubles both as an easy way to test the input and output of a function, and it serves as documentation. Additionally, if you space apart functions into smaller bits across multiple different files, it means that if one thing goes wrong, you don't have to redefine every call or every instance of that throughout an entire gigantic bloated file. You can simply fix this sort of symbolic cog in the machine that is my framework. Now, another thing I learned is that race conditions are bad. They are very, very bad. The price we pay for being able to utilize parallel programming is that we have to worry about race conditions. It might be the case that 2 threads that could contest against one another, that could cause issues, they don't always fail every time. It could be that 2 threads, for example, write to the same .mod file because 2 programs are defining the same module. So in one case, one thread writes to the .mod file, completes, and then the next thread writes to that same .mod file after overwriting it. And so that .mod file is going to be just fine. So if a program later on references that .mod, it should most likely work out. But if 2 files are writing to a .mod at the same time, then if a file later on tries to reference the jarbled mess that is that bot.mod, it will encounter a lot of errors. So this means that testing is sporadic, and if testing is sporadic, the results are sporadic. If the results are sporadic, then cross-checking becomes moot. It's also very important to read the documentation. This was something I learned in Make, with the usage of Make. I found myself almost confused with the idea of being able to both run Make in parallel and then translate its output into a means by which I can parse through it and effectively compare 2 results. But simply going to the documentation available online from the official source made it so I could just read through each of the flags and understand, oh, okay, I gotta combine these 4 flags together with the usage of Make in order to facilitate proper runtime for both pre, post, and during tests. By making your work legible and well documented, you help out everybody involved. So this includes people that might download it and work on it later on, but it also includes yourself, because by commenting everywhere and translating the abstractions present in your code into cohesive written English instructions makes it so that someone else can look at your code and understand its functionality, but you also, along the way, remind yourself of what you intended to do when you sat down and created such and such function or such and such class. And in a more practical sense, I have gained a more intimate understanding of Python itself. I've used Python in ways I never used Python before, and I was working with data that of such magnitude that I had never encountered in simple academic settings. I've also familiarized myself with two new languages, Bash and Fortran, which I think is pretty cool. Especially Bash, because Bash is a very powerful scripting tool for somebody who uses it. So moving forward, there are some things that need to continue to be done using this framework. So test results should continue to be sent to Intel. There were some bugs encountered, and they were sent up, but further usage of this framework should be facilitated, and consequently, these results should be sent to Intel. In fact, this framework, when it comes down to it, is simply just a cross-check between two compilers. So if some other group or company out there wanted to decide to make their own Fortran compiler, then they could test their compiler using this same software and see for themselves what errors they might encounter. The framework also, in plain terms, could always use more files for testing compilation. At the end of this, I had about 3,000 to 4,000 files present to test against, but why not 6 or 7? Why not 10 or 12,000? It's always useful to have a bigger pool as to lessen the margin of error. And ultimately, the outcome. So the framework is completely open source, so please send pull requests, whether that's somehow editing my code to make it better or including your own repo of Fortran files. And as I said before, there are about 3,000 files downloaded and tested using this framework. And we reported multiple entry point bugs to Intel, which you saw in the IFX behavior slide. So ultimately, I'd like to give a special thanks to the laboratory for providing me this opportunity and this internship, and to Thomas and Colleen for their incredible patience, knowledge, and encouragement throughout the creation of this project. And with that, I thank you all for attending and listening, and I'm glad to take any questions that you might have.
Thank you, Augustine. You see, we are trying our best to form the next generation of Fortran programmer. So this is our contribution to the HPC world. So does anybody have some question?
Was there any reason why you chose to validate against gfortran instead of like ifort or like gfortran or any other Fortran compiler?
Well, we had initially understood that gfortran was simply a good Swiss Army knife of stability. It rarely encountered bugs that IFX encountered. In fact, by the end of it, I had multiple directories with multiple files included in them, a good amount of files included in them, and gfortran was able to compile everything perfectly, except for files that had errors innately. So we simply used it as an example of a stable compiler, but we sort of realized towards the end that we could have also used IFX just as well.
So which version of gfortran did you use?
Which version of gfortran did we use? I'm actually not sure. Thomas, do you know the answer to that one? I'm just using
9.2.
Yeah, 9.2.
The one in spec.
Yeah, the 9.2. But yeah, I think to answer Paulus' point, yeah, it was, or I don't know why I chose, it was my call to use gfortran, because naively I chose GCC to give the correct answer and to be more spec compliant maybe. But realized during some testing that, yeah, gfortran and ifort and IFX have really different interpretation of the standards. So at some point we compare IFX and ifort, the two output, and the only difference we saw was this alternate entry were causing some issue, some IC. But it's not, it looked like IFX and ifort, at least for the compilation, behave the same way, give the same warning at the same time and everything. And the compare.py was really nice to be able to compare all the warning and to be sure that, yeah, both compilers behave similarly.
Okay, so if you automated this process, you may have more references, right? So yeah, as Paulius asked, he's from Intel, so he's asking why not use Intel Fortran. So we know there's no perfect compiler. So if you use gfortran, ifort, and the Clang as a reference, and then automated the process, that'll be really quick. Right now, it's great, but just comment.
No, yeah, that I hadn't even thought that. That's an excellent point because again, you can't necessarily rely on a piece of software to be absolutely perfect in every instance of its usage. So, as you've said, if we were to blend the usage of compilers such as gfortran, iFortran playing together, then we could create supposedly a more stable outcome there. I also see a question in the chat asking 3,000 files from where. So most of the files I used were downloaded using the scraper that Thomas and I created. And a huge bulk of them actually came from NASA itself, a bit over half of them. But a couple others came from certain like university repositories, such as one from Florida State, if I remember correctly. Yeah, I had attempted a couple of weeks ago to try to add more Fortran repositories from the internet, but it turns out a lot of them are no longer hosted. So yeah.
Why not target DOE Fortran codes instead of random codes on GitHub?
Well, the advantage to targeting random pieces of code that you might find on GitHub or on a university webpage is that these are simple, small-scale programs. Like, we simply want to find just, like it might when a lot of these programs have several lines of comments found in them. But if you were to remove all the comments and all the extra spacing, the program itself might boil down to something that's 20 or 30 lines long. It was better we decided to test several files that were simple than a smaller pool of files that were more complex. Does this necessarily mean that Fortran code found from Argonne itself are innately more complicated? Not necessarily. But simply just for ease of access, and we already had the scraper available, we decided to use code from online.
Yeah, and I think the way Augustine designed the testing framework, it's easy to add in applications too. So we can probably extend it in the future to get more complex applications to wider coverage.
There was actually sorry.
Yeah, and as you know, installing and testing really big science DOE application can be a little tedious. And I didn't want for Augustine to spend his time just learning how to install code. I'm not sure it is the best way for a learning experience to try to install large Fortran application. But I think it's totally a valid point that we should, after, try to expand and to try to put more tests. So, for example, we already have a test set for more this kind of application. So if you have any application you want to be sure it compiled with IFX and everything, just send it to us, and we can take the pain of installing it and to be sure that it's running. Yeah, it works.
There are actually some. I'm sorry to cut you off here. But there actually are some tools available in the repo that I hadn't mentioned. This includes critically for your question. This includes an add new bash script, which simply, given a path to a directory containing whatever Fortran files you might wish to import, you can use this bash script to import it into the source file of this repo, which you can then use in future testing. There's also, importantly, a verify.py Python script, which parses through all the files in every directory and attempts to find if there are conditions necessary to create race conditions. Importantly, this means if two files define the same module. So if you wanted to add in your own set of Fortran code, you could fork the repo from GitHub and then use this bash script to just add your directory into the framework and then submit a pull request. I encourage everybody to do that because the greater the pool of files, the less margin of error occurs.
Okay. Can you put that slide up again?
Which slide in particular?
One with the repo on it.
The one with here.
There you go. Mm-hmm.
Let's see here. How many of the I'm reading this from the chat. How many of the object-oriented features of Fortran did you test? So I was again, I'm not an expert Fortran programmer, unfortunately. But the four main, as I understand your question, the four main structures I was testing for were subroutines, interfaces, modules, and functions. Modules in particular were very important for this project when it came to, say, the make file generation, because it was use calls and module calls that basically defined how in a directory these dependency trees might be created. Does that? Sorry,
Yeah, to answer the question, I think none. I think none of the tests
Classes,
did
classes or anything.
I think it's because it was both random and conscious choices, because at the beginning when we started this project, IFX got lot of issue with all the Fortran 77 code, because it looked like Intel didn't have a large pool of all Fortran 77. So I try to target the repo we find into all the kind of old school Fortran, so a lot of NASA or some people, computer scientists, Russian computer scientists who put all their routine to compute really mathematical stuff inside. So I don't think any of them. And strangely, it's easier to find old Fortran 77s than the recent Fortran 2003 online, at least in the public. So yes, this is why. And to answer Victor, no effort at all. It's just we found everything what we found online, because I think in this approach it was more like a kind of a big data kind of approach. Let's try to take the maximum number of simple Fortran files who is easy to compile and see if any one of them crash. Right? So for example, we don't run them because one of them is really hard to automate, like the testing, the validation of the code. So most of them we just download and hope to don't have any ICE or some warning and everything. It was really not a test suite. We try to find some test suite online. I know some old company have a large set of test suite, conformant test suite and everything, but it's really hard to find nowadays. I think maybe if some people have some copy, I think it was I don't remember the company who have a large conformant test suite. Neg, yeah. So if people have that laying around, please, if you can send it to us so we can try to run it.
Yeah, again, you should be able to add hope tests somewhat easily, so we can always extend this to test more.
If you have questions on how to use the add new script or any of the bash scripts I include in the repo, then I tried my best to lay out instructions very clearly for each of these in the README present in the directory. Otherwise, I mean, you're always free to shoot me a message on GitHub or email me.
Do you have any more questions?
Yeah. So I was wondering if you had considered trying to capture some of the compile timing. And then also, like, from a high level, did it seem like IFX was comparable to GFortran in terms of, like, how long it takes to compile all this stuff? Obviously, there's a little difference on the high level with things breaking. But
Right. So I had actually, at one point, attempted using something as simple as time to test how quick it was to run my test using GFortran and to run my test using IFX. So each time you run the test, it not only uses the compiler in question, but it also makes clean in order to wipe away executables created from the previous runtime. But with that in mind, with all conditions set equal to one another, I didn't find any significant differences in timing between GFortran and IFX. I think the greatest difference in time that I saw was the difference between it being, I think, about 35 and 36 seconds and for GFortran and 44 seconds for IFX. And this is for compiling all of the files present across all the directories. And this is using parallelization. are there any other questions that people might have?
So I have a soft question. So do you plan to come back next year?
I would absolutely be honored to do that. Argonne, I mean, this isn't necessarily to the functionality of the framework itself, but Argonne has really been an incredible opportunity for me, and I've learned a lot here with Thomas and Colleen. Like I was very lucky to be given them as my mentors because they are incredibly kind people and very, very well informed on everything. And I also got to take a lot of these concepts I learned from class that had originally just been abstractions, like, oh, you could hypothetically use depth first search to do whatever. But here I actually got to apply it. Ultimately, it wasn't actually necessary to use depth first search for the construction of make files because make actually does it for you as long as you define the first level of dependencies. But it was very cool and very satisfying to see that I was taking these concepts I had learned in classes such as algorithms and data structures and software design and turn them from just abstractions that a professor tells me about and assigns homework for into something where I'm actually applying it to something that feels relevant, you know? I mean, Argonne is super cool because it's like I'm not just working for some random corporation where I further the interests of a corporation. I get to work for what I believe is like the good of scientific progress. And I'm very honored to have been doing that with Argonne and to be able to contribute to open source on GitHub.
Yeah, I think it's a work environment. It was really nice.
Okay.
No, yeah, I know. I think it was really nice to having you and to you are really easy to work with and try to.
Yeah. Put things out on your own and stuff.
And I think I don't know for the question for the new LLVM Fortran if you speak specifically about Flang.
Yeah.
I have no idea about the cap. I know Brian maybe you know more.
Yeah. I mean it exists, but maybe it is enough. But I mean it might be useful. We might be able to put our tests into it at some point with the LLVM testing work. But
yeah, I think we can try.
But I don't know if Brian wants to comment on Flang itself.
Yeah, I mean, it sounds like you should be able to add it into this. If you're talking about like the brand new one that's going upstream in LLVM, which was like formerly F18, I haven't followed it too closely recently. I know they were kind of going breadth first development, so I'm not sure what state it's in.
Yeah, maybe one good thing of this test set is real code that real people write. So sometimes you have really like non-conformant. For example, the error when that Augustine show with the 7 and after the subroutine, the standard specifies that you need to make a space, right? You cannot put the label directly without space to the name of the subroutine, but iFortran doesn't care. But gfortran was complaining, so it's always nice to have this kind of to know the difference, at least if you want to teach your user in your cases, or if you are a developer to know that your code will not be portable. So, and be able to check between IFX, Flang, whatever, gfortran and IFX can help people try to see and maybe, to be more portable.
It was actually an interesting side note about that. I had originally expected that or something like IFX, which is still in development, that when I actually generated these tables comparing what differences occurred in each given compiler, that there would only ever be results on the right side. That the only errors that were occurred by one and not the other occurred in the bleeding edge compiler. But actually, as it turns out, in the case of that typo, it's possible for gfortran to run into a bug that IFX does not. And that is imperative to understanding the development and the functionality of both compilers. It doesn't necessarily mean that gfortran is innately less stable than IFX, even though that is what my approach originally had hypothesized. but rather that IFX or that gfortran just accounts for more human error than IFX did at the time that I developed that, at the time that I was testing it.
So in the Fortran world, the Cray is also could be a good reference. Yeah. For C compiler, I don't have any.
Yeah,
Fortran.
yeah.
Right.
Yeah, Cray is maybe too much. Yeah. If
Right.
you compile with Cray with pedantic, if you don't finish your line with an empty line, you will complain that it is not spec compliant. So maybe Cray did go far too much in the compliance thing, but yeah.
Alrighty, are there any other questions?
So going forward, will somebody at ALCF be running this every time there's a new IFX compiler drop?
Yes, exactly.
Yeah, I think,
So
we will incorporate it.
yeah, so we have already a test set that we run at each IFX drop and everything. So right now how it's works is like if you have a bug in IFX, you can just send it to a reproducer. We'll put it in your test bed, and we'll check that we don't see any regression, and we'll notice you if you when this bug is solved. We also put a few select ECP application, and we incorporate all of these tests in our test base just to be sure that they will never broke. So it was the goal of this project to be able to, for LCF or Argonne, to have a more robust test. So we are sure that when Aurora comes, we'll have a good Fortran compiler, and not only for ECP application, but also for this kind of strange Fortran 77 written 20 years ago, or maybe also if you have really new Fortran 2003 features that you really want to us, you can just please send us an email so we can put it here and to be sure that we got it working.
Or just send a pull request. You can do that too.
Yeah, as you want. Yeah. Yeah, it's a good question. We run only with O0. Default flag. So maybe I think it's not the same between gfortran and IFX. So maybe what we can try is indeed do multiple paths with multiple compiler flag, like at least fastmass or whatever the equivalent is, and maybe between O0 and fastmass, at least to run. I think it's a good idea to see.
So, Kevin, thank you for your question. Wow. After I graduate, well, I guess it's
Don't say you want to work in finance or in hedge funds.
Bitcoin.
No, I do not want to work in finance. No, absolutely not. No, I want to somehow apply what I've learned at school and at Argonne, something that affects a lot of people, which does and does not answer your question. If that is found at a facility like Argonne, then I would be almost boggled, because I guess attests to my own growth as a software engineer from the time where I was in freshman year and was, pretty okay at it, to now when I think I'm, pretty okay at it. Yeah.
Oh, that's cool. No worries about like what your answer is. I think at this point it's fine not to have decided on anything. But just the fact that you're thinking about it and you have an idea where you want to go, or like a general picture of what your life will look like, I think that's already a great thing to have.
Yeah, totally.
Yeah, I'm still not sure what I want to do in my life, so I think you have time.
Yeah, me too.
So, thank you very much. It's noon soon, so please have a good lunch, take a rest, and thank you again, Augustin. It was nice, and I will send you your Argonne mug when the cafeteria will open at some point. Or
Sure.
I will steal one from somebody at the office. Nobody's here, so.
Yeah, okay, I'll take you up on that. And thank you to everyone who attended this talk. I greatly appreciate your input and your questions, and I hope that my work can be expanded upon by some of the people who work here at Argonne. So thank you so much for attending this talk, and I hope you guys have a good rest of your day.